researcher at the Institute in Copenhagen, and he also recently was hired as a professor at Penn State University in the US, and I understand right now he's still on another appointment, so still half a year. So please, thank you.
Thank you very much. Let me turn on the microphone. Thank you so much. So as you can tell, this lecture and the next two lectures will be Blackboard, and so I encourage you to come closer if you'd like. And the outline is, today we're going, after I have some introductory remarks, I'm going to talk about, this is really like amplitudes kindergarten, very basics. Some of you have probably know this very well, but it'll just be to remind yourselves of the basic building blocks about what's nice about especially massless theories in 4 dimensions, and it'll lay some groundwork that'll be very useful for us going forward. Tomorrow we'll talk about taking these building blocks and building them together into things called on-shell functions, and particular S matrices we'll derive on-shell recursion relations. And then in the third lecture we'll understand how to classify these things and really build a combinatorial framework suitable for Yang-Mills at tree level and for n=4 at all loop orders. The basic references for this, especially these first 3 lectures, can be found in this archive paper and this paper. The first you can also find if you'd like to send me some royalties in this book here, and we'll be covering the first few chapters of that. Lecture 4, which will be on Friday and will be the last lecture apparently, will be a very kind of different kind of lecture. The goal will be to we'll start off by deriving what the recursion relations look like in a special set of kinematic variables called momentum twister variables, which are very well suited for planar n=4, which therefore also for Yang-Mills at tree level. And the idea there will be to open up a blank notebook in Mathematica and to walk you through the development and internal testing of code that will give you all 3 amplitudes in Yang-Mills. And so you don't need to be familiar with Mathematica. I'll be talking my way through it as we go. But it sometimes feels a little bit more like performance art than a lecture. Okay, but before I get started with the bulk of this talk, I thought it would be good to kind of set the stage and explain some of the reasons why you might be excited about studying scattering amplitudes right now. We're in a pretty exciting time. And I think for me at least, the 2 motivating facts behind why I'm excited about scattering amplitudes are that quantum field theory is hard, which is something I think everybody in this room already knows. It's hard on every level. It's hard on enumerating contributions. It's hard doing loop integrals. It's hard across the board. And yet, when we make predictions for experiment, or whether it's a real experiment or an imaginary one, the predictions themselves are always very simple. That's fact number 2. Now, those 2 facts together imply a corollary, which is that quantum field theory is harder than it probably should be. If every time we break our backs to make some computation, make some prediction for experiments, we get mocked by the simplicity that we find, perhaps we should revisit the basic framework. And indeed, in the last 20, 30 years, there's been quite a revolution in our basic underlying principles. And which is why whether you're trying to make connections to experiments, like at the Large Hadron Collider, or you're just studying purely theoretical things, you'll find yourself studying some of the modern methods. And in these lectures here, at least in my lectures, I'm only going to scratch the surface. There's a great deal of knowledge to be had, and there are lots of new tools. And what's exciting about this is that these new tools are really, with few exceptions, beyond the scope of standard textbooks, which really haven't changed very much in the last 30 years or so. And so we're at this exciting time where a really foundational subject, quantum field theory, important to the foundations of theoretical science, and hugely important for experiments and for our theoretical understanding of the universe, is this mature subject is at a state where all of the textbooks we have are a little out of date. And that's exciting, because it means that we get to play a role in writing the future generations of textbooks. So to give you an idea about what this discrepancy between the difficulty of making predictions for experiment and the kinds of predictions we find, there's a classic example that I'm sure you've all heard of, but I'm going to review again because it's so, I think it's foundational to at least my worldview in the subject, which is a practical calculation for collider physics, which is just the production of, say, 4 jets given 2 jets, something. So this is a classic thing by Park and Taylor. They studied the question about what happens when you collide 2 gluons and you create 4 gluons there. And we can represent this pictorially, and for the sake of you guys are experts here, let's say that they're all minus Felicity. So 2 minus Felicity gluons create 4 minus Felicity gluons. And we can represent this process with some kind of dash blob, say particles 1 and 2, and this will be explained in a lot more detail here. So minus Felicity goes in, and you create 4 goes out. Now, when 2 gluons create 2 gluons, that's a homework assignment in a quantum field theory class. It's not that difficult. It's a little bit of work. In fact, it's a homework assignment you probably should have done in a quantum field theory class. We're going to label them 3, 4, 5, 6. And there's something about color that I'm glossing over right now, but we can come back to that later, especially in this lecture. Now, 2 gluons create 3 gluons is a research problem, or at least it was once in the early 1980s. And why? It's not actually that bad. It's only 25 Feynman diagrams. You can almost do that on pen and paper. It's not really that difficult. But 25 Feynman diagrams gives you a few pages of algebra. It's kind of an ugly mess. And 2 gluons create 4 gluons was once considered not even a research problem, was once considered beyond the scope of conception for what theorists could reach. And you know, from a modern point of view, it sounds a little bit silly because it's 212 Feynman diagrams. Okay, well, you're not going to do that on pen and paper, but we have computers. And sure enough, Stephen Park and Thomas Taylor put their backs into it, and they used all sorts of clever tricks. They didn't just use the Feynman rules. They introduced n equals 2 supersymmetry just to relate it to a different amplitude. They didn't want to compute the gluonic one, just to relate it back, you know, lossless. And then they used lots of modern sophisticated techniques, and they rushed the thing, and it got 8-page expression. They were very proud of this and rushed it to publication. The cross-section for 2 gluons to create 4 gluons is given in a form suitable for fast numerical calculations. Okay. And as I'm sure everybody in this room knows, a few months later, they discovered that that 8-page formula could be written as 1, 2. I'm going to explain this notation in a little bit, but this is 3, 4. There's a clear pattern here, 4, 5, 5, 6, 6, 1, 1, 2 to the 4th. Now, that's an impressive feat to see 6 pages collapse into 1 line. But what's infinitely more impressive is that it naturally suggests a guess for not just when 2 gluons create 4 gluons, but maybe when 2 gluons create any number whatsoever. So let's say it goes to n, we can say here, and there's n minus 2 produced. And the natural guess is that all we do is we just write dot, 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 n1. And this, as a claim, is truly incredible. When 2 gluons create 50 gluons, the number of atoms, the number of Feynman diagrams at leading order of perturbation theory, just a leading order, exceeds the number of atoms in the universe. It's like 10 to the 84 Feynman diagrams. And so here's this claim that if you added up all those 10 to the 84 Feynman diagrams, you'd get one simple function. And I think this is should be viewed as an indictment on the Feynman expansion. Now, of course, we all know and love the Feynman expansion. It's hard for us to forget it. It's very intuitive. But by the end of the second lecture, we'll derive this. We'll be able to prove that this, using the way that it was actually first proven. So we will prove recursively that this is the case, which is one of the nice consequences of having a new perspective. Feynman expansion will never make this kind of thing, this kind of simplicity manifest. Now, of course, this is just at tree level, and of course, there's higher orders. But I want to also emphasize that the problems with the traditional formulation of quantum field theory aren't really limited to tree level. They're not limited to, and quantum field theory is hard on many more levels. So another example that I hope everybody is very familiar with is the gyromagnetic ratio of the electron. So this is not really an amplitude, it's more like a ratio function, but we'll say, so this is something you've probably also seen in your quantum field theory course. At tree level, there's a single Feynman diagram, and this would give the theoretical prediction, I should write theory here, as 2. Got Dirac his Nobel Prize. And at one loop, there's also only one Feynman diagram. And I hope most people in this room have done this calculation as a homework assignment. We usually give it as a homework assignment, and it's about a page of algebra. And at the end of this page of algebra, you get an integral, which if you just put into Mathematica, it doesn't know how to do. Okay? And then if you learn some clever tricks how to massage that integral, and then you can get it, and what do you find? Well, there's a prefactor here that had to be there, alpha over pi times 1. So you did a week of homework to find the number 1. Okay. At next order, at two-loop order, you get that. It's, again, this, by the way, this got Feynman, Schwinger, and Tominaga their Nobel Prize. This didn't get anybody their Nobel Prize, and it took 10 years to do. There's plus 6 more terms. And the correction is alpha over pi squared times 3/2 zeta of 3 minus pi squared log 2 plus zeta 2 plus 197 over 72, I think, plus dot, dot, dot. And you start seeing, now, this took 10 years to get from this line to this line, numerically, done by Peterman, I believe. And this analytic form, I believe, was first found by Laporta. And it's been continued. So starting at 3-loop order, there's 72 Feynman diagrams. Not so bad. You can put that on a computer. 72 is not so bad. So there's one Feynman diagram, but that integral takes you a week. You know, then there's 7 Feynman diagrams. It takes you 10 years. Get this. The next level, there's 72 Feynman diagrams. That took, 20 years or 30 years? Wasn't done until the 90s. At 4 loops, which is now also known, oh, by the way, so starting at 3 loops, you start finding some interesting number theory there. And I'm sure that Johannes, in his lectures, will start talking about these zeta values that appear. And so you start finding unusual zeta values. So they're not really, well, they're not simple zeta values. You find more unusual numbers like Li4 evaluated at half, things like that, at 3 loops. And at 4 loops, you start finding some really unusual numbers. So Laporta's computed this to over 4,000 digits, every single contribution, and all these 891 Feynman diagrams at 4 loops. And you start finding some really unusual numbers, like periods of K3 Calabi-Yaus, 2-dimensional Calabi-Yaus start appearing. Numbers that we don't really have in the framework of multi-zeta values. And you also find elliptic multi-zeta values, which are now in a framework that we understand. And if you go to 4 loops, or 5 loops, which has been done numerically by Kinoshita, we're talking 12,672 Feynman diagrams. Okay, now I'm more familiar with the 4-loop one because there's some really brilliant paper, because Laporta recently, in the last few years, revisited this and really cleaned up this thing so that we understand the few missing bits, these weird Calabi-Yau things, they know to 4,000 digits. But all of the other ones are really understood and to infinite precision, which is pretty remarkable. And one thing you might notice that if you look at this 891 Feynman diagrams, they're all of order 10,000. Now some of you might not know what the actual correction to GE is. So we find 1. This number is like minus a half or something. After that it's 2, and then it's about 4. At 4 loops. It's about 4 again at 5 loops with some alternating signs. But so you already see that adding up 891 Feynman diagrams, we're talking cancellations, incredible cancellations, 10,000, order 10,000 numbers all adding up to an order 1 number. That's kind of surprising. Well, I'm not really sure if anybody's ever actually added all those up. And the reason is because it was noticed long ago by, and I'm not sure if I'm giving credit exactly where it's supposed to go, but Predrag Cvitanovic pointed out long ago that if you added that it's kind of a bad idea to add up all of these Feynman diagrams. In particular, it's a much better idea to add up gauge invariant subsets of Feynman diagrams, to group them into groups where you had where full S matrices appeared at vertices. And if you consider how many gauge invariant collections of Feynman diagrams are there, at 3 loops instead of 72 Feynman diagrams, there's only 6 gauge invariant groups that you need to compute. So you take these 6 things. And at 3 loops instead of 891, there's 13. And at 4 loops, it's 32. So 32 is a lot smaller than 672. It's probably a good thing to do. And I'm not sure if this, well, it's pretty clear if you read those papers that there was definitely an idea that grouping things into gauge invariant subsets was morally a better thing to do. And indeed, the cancellations are better. So if you look at 4 loops where you have these order 10,000 Feynman diagram integrals, if you look at the gauge invariant subgroups, it's order 10 each. Now still, adding up 13 numbers of order 10 to get an order 1 number is still some cancellation. There's still some magic there to be explained. But it was already a good idea. And this idea of grouping things into gauge invariant subsets is very similar in spirit to something that I think has laid the foundations for a ton of the progress that's happened in quantum field, in the amplitudes revolution, which is under the guise of generalized unitarity. And I'm not going to have time to really do this justice, but we are going to come back to more of these building blocks. But the basic idea, unitarity, it's intellectually different. I don't think there's a connection directly with the G-2 kinds of calculations, but it's basically formalizing that idea that you don't want to compute things that are gauge dependent. And instead, if you try to look at the sum of Feynman diagrams as a rational function, that you could group them into gauge invariant subsets. And the simplest one would be the unitarity cut. So something like this, where you look at, where by a picture like this, I mean an S matrix and an S matrix with on-shell particles here. And one way to define it, I'm going to define it in a few more precise ways in the next lecture, but one way to think about a diagram like this, or what I mean by a picture like this, is that you look at all the Feynman diagrams, you fix the external legs, you look at all the Feynman diagrams that have this topology as a subgraph. I don't actually mean a subgraph, I mean as a quotient. And if you quotient by edge collapses, you add them all up and you take the residue putting this particle on shell and that particle on shell. I said it that way just so I don't have to tell you the labels of how the loop momenta are routed around. But you can do the same thing at higher loops, and it can be non-planar, it doesn't matter. If we have a picture like this, again, the meaning of a picture like this is you take all the Feynman graphs for some process. You have to specify the loop order. Say that you're at 3 loops so that every vertex here is a tree. And you add up all of the Feynman diagrams that have this topology, and you take the residue, putting everything on shell. And basic principles of unitarity and locality that we're going to review in this lecture mostly dictate that this has to be on fully gauge invariant, because these vertices are full tree amplitudes, and the products of all these trees are gauge invariant. And so you start getting, so the output of generalized unitarity is a reformulation of the perturbative S matrix in terms of funny looking pictures like this, which are called generalized cuts, which are built out of gauge invariant building blocks, times integrals that have a whole story on their own. And you can glue them together and reproduce perturbation theory without gauge redundancies. And if you applied this kind of philosophy to G-2, you would reproduce the smart perturbation theory, which is what's been used by everybody. You'd find the 13 Feynman gauge invariant subsets instead of 891. And you'd find the 32 instead of 12,000. So that kind of idea. Okay, now a big picture, again, before I really get started, I'd like to think about this whole program, the scattering amplitudes program, as something of a virtuous cycle. And we've already seen some nodes on this cycle here, but a virtuous cycle. So it's a cycle, so I can start anywhere I'd like. But let me start with this. So the first step, you compute something. And you compute it for whatever reason. It's something hard. It's usually pretty hard. Maybe you're Park and Taylor and you're trying to match to experiments like what they thought was the soon to forthcoming superconducting supercollider. So maybe you're motivated by matching to data. Maybe you're motivated for purely theoretical exploration reasons. But you compute something hard. You put your back into it. Okay. And then, invariably, and this is where all of the magic really happens in this whole game, is that you discover something. You discover some simplicity, like a formula this short, that might take you decades to figure out why it is. But you discover something. And there are so many examples of this in our business that this is really anytime somebody's computed something hard, we've found something nice. So there's something, when we stop discovering things, this cycle may end. But at the moment, there's no reason to see it stopping. So you discover some simplicity. And sometimes that's done by the same people who did the computation. Sometimes it's done by other people. And sometimes it takes a long time. And then you understand it. Understand. Now this arrow can take quite a long time sometimes. In the case of Park-Taylor, the understanding, the proof that this was the right answer, it could be argued slightly differently, but I would say that it wasn't proven until 2004. So about 20 years it took for anybody to prove this, as we're going to prove it in the next lecture. And once you can have a proof of it, then you understand why it's simple. And understanding then quickly turns into exploitation. Exploit. And what I mean by that is that you then take this understanding and you build it into your basic toolbox, how you go about computing things. And by making this kind of simplicity manifest, once you know that 2 particles creating 50 is a single line expression, you can feed that into a little corner of one of these things, and you can go way, way, way further. So by exploiting it, I mean really building it into technology. And once you have it built into technology, both your understanding and on a computational level, you go back, and the cycle repeats. And scattering amplitudes, I think the history of our understanding of this subject can really be viewed as kind of walking around the circle again and again. And there's many, many examples of this. And if you stay in this and you become amplitudes researchers, some of you, of course, are, already you'll find yourselves at different nodes at different times. Sometimes you're calculating something. Why? Because you can. Maybe because somebody needs it. Maybe you're trying to make a connection to gravitational waves or something. You'd have some serious reason to compute something. And then you discover something nice going on, and you keep going. So this is what keeps me excited about research in scattering amplitudes. Okay. Okay, let's get started. So like I said, this lecture is really going to be elementary. I'm going to really start at the bottom, kind of an embarrassingly low bottom, so please forgive me in advance. And we're just going to talk about what a scattering amplitude is a function of. And although a lot of things that I would like to say don't have very much to do, like unitarity, for example, has applications way beyond 4 dimensions, way beyond massless particles, and there are a lot of very beautiful things that we understand out of that. There is a lot of things in the next few lectures, especially my lectures, that are restricted to massless theories in 4 dimensions. And so, unfortunately, for better or for worse, if I don't specify it, I'm talking about massless theories in 4 dimensions, which happens to include a lot of theories we're interested in. But it's because in this case, there's a lot of extra magic. There's a lot of extra understanding. There's a lot of extra magic that we know exists. It doesn't mean that it doesn't exist elsewhere. It means that we just have found it and we've explained it in 4 dimensions. There. So let's talk about what an S matrix is a function of. So physical states. And this is really, by this I really mean, what are the things that an experimentalist will measure? How would they describe the process in some experiment? Whether it's a real experimentalist or an imaginary one doesn't really matter. I just mean, what are the states, what is the S matrix a function of? And I'm not going to allow any answer that involves a Lagrangian or fields, because we don't see fields. And notationally, I'm going to say the S matrix, in particular the tree level. When I have something to say about loops, I'll tell you. But it's just going to be some hatched blob like this. Hatching because there are, I'm going to need some other notation for some other cases. So, and at tree level, it doesn't make much of a difference, but for the sake of clarity, I'm always going to be, I'm going to always label my states on the outside clockwise around the graph. But again, at tree level, it doesn't really matter, and I'm just talking about a function of n particles. So, the physical data for the 8th particle, and I'm going to use lower Greek indices, or sorry, lower Latin indices to label the n external particles always. So for the 8th particle, there are several things that we need to describe. So what is A a function of? Now, the first is the momentum. So PA with a Lorentz index mu, and this is not a free d-dimensional vector, but it's subject to one constraint. So on mass shell, so we usually don't really talk about this, but on shell means satisfying this equation that P mu A P A mu is m squared for the 8th particle. So this is a bit of silly notation, and it's unfortunate because when you try to explain to, say, a reporter or somebody outside of science, like what's up with the on-shell S matrix, and you have to explain, well, on-shell means that it's not off-shell, and then you have to suddenly explain that, and it's very confusing. But this quadratic equation here, p squared equals m squared, defines a hyperboloid, and that hyperboloid is called the mass shell, and if you satisfy this is just Einstein's equation. If you satisfy this, you're on the mass shell. And it's unfortunate that we have this like on-shell part of our language because it should really just be particles or observable states. Every particle you detect in a detector will satisfy this equation. Okay. Okay. So it's subject to one constraint. Also, and now this is where I'm going to get to 4D because I don't want to carry around big D's everywhere in my equations, but you know what the representations of the Poincare group are. But we have spin / helicity, which are related. In 4D, we have that the helicity of the 8th particle runs from its plus its spin to its spin minus 1, ... to minus its spin. For a massive, ma not equal to 0. And for a massless particle, it has to be, well, I'll just say is equal to plus or minus the spin of the particle for massless. So we have these degrees of freedom. Notice the Lorentz indices on here. These are discrete quantum numbers that label the state. Okay. And then there's a whole lot of other quantum numbers that I'm going to call non-kinematical. These are kinematic quantum numbers for sure. And they're related to the Poincare group. And then there's all sorts of non-kinematic labels. which I'll collectively denote as QA for the 8th particle. And by this I mean the color of the particle, the species, the flavor. You know, when you want to distinguish between the tau neutrino or the muon neutrino, you know, you have a label for that too. So I'm not going to call that a kinematic label. Of course, if they have masses, it's kind of mixed up with these things too, but let's ignore that. For the moment, for most of this talk, for most of these lectures, I'm going to take the case where we're massless particles with these plus or minus felicities. Now, if you open up most quantum field theory textbooks and you compute an S matrix using Feynman diagrams, this is usually not the kind of thing that you find. You don't usually find a function of momenta and helicities. In fact, helicities usually don't appear at all. What do you find? Yeah? Polarizations. Now, I'm not listing polarizations here because an experimentalist does not measure polarizations. Polarization is what the experimentalist measures is helicity, the amount of spin pointing in some direction. They can measure that. But the polarization is a redundancy in a very different kind of redundancy. It's a different kind of redundancy. It's not just a constrained quantity like this, but it's subject to a whole equivalence relation that's related to the difficulty, or it's related to the requirements of writing down a local field theoretic description inside a Lagrangian. In order for you to write the field of the photon at every place in space and time, you need a Lorentz index. And having that Lorentz index forces you to talk about a polarization with a Lorentz index. And so you might say a epsilon a mu, and you might say subject to with epsilon a mu dot pa mu equals 0, sure. But for a photon or for a higher spin field, there are extra redundancies here. And those are associated to on-shell Ward identities. That's equivalence relations. So for example, in QED, we don't just require that it's orthogonal to the momentum of the particle, but we actually say that epsilon a is equivalent to epsilon a plus any function of pa times pa. And this functional equivalence, so this whole field, we're defining a field of this everywhere in space-time, and we're defining it to be equivalent to another field that's a very different function, is gauge redundancy. And depending on, there's a beautiful, you know, gauge theory is a very beautiful mathematical subject in its own right, and it definitely came about by understanding the constraints on consistent quantum field theories at the Lagrangian point of view. But one of the things that I hope to prove by the end of this lecture is that when you talk about massless spin 1 particles, there's nothing but gauge theory. And it doesn't have anything to do with redundancies. We will show one of the outputs of towards the end of this talk will be a proof that any consistent quantum field theory involving spin 1 particles, the spin 1 particles, their other quantum numbers have to form the adjoint representation of some Lie algebra, having nothing to do with Lagrangians. And you can similarly find, we'll also mention the equivalence principle for spin 2 particles. So from a Lagrangian point of view, introducing polarizations and then figuring out which Lagrangians will give you Feynman rules that satisfy on-shell Ward identities is a very complicated restriction on the space of Lagrangians. We'll see more or less from first principles that just talking about an on-shell S matrix and restricting our language to these simple physical states will immediately give us the uniqueness of Yang-Mills and gauge theory and relativity, or linearized relativity for spin 2 particles. Okay. Now, for massless theories in 4 dimensions, there is a very good description, which is to make this property, so if p equals 0, there's a very nice formalism to make this manifest. By the way, so there are a few other things that we should talk about here. So the set of momenta on which this depends usually is subject to a constraint of momentum conservation. And that momentum conservation, if we take all the momenta to be incoming, will be that the sum of the momenta is 0, which is the same constraint if they're all outgoing. So there's an extra constraint here. And so the S matrix is a function of these p's subject to an on-shell condition and momentum conservation. These 2 extra constraints are kind of in tension with each other. You can make one of them manifest, or maybe the other one, and there's one set of variables that lets you make them both manifest that we'll get to in lecture 4. But for the moment, let's leave momentum conservation as a non-trivial constraint and just talk about this on-shell condition, trivialize this as much as we can. And that can be done in terms of what's called the spinor helicity formalism, or spinor variables, which goes back quite a ways to van der Waerden in the 1920s. So spinor helicity formalism. So the basic idea here is kind of starts from a trivial observation, that instead of writing a 4-vector p mu, we instead think of a 2-by-2 matrix, p alpha alpha dot, which is defined by dotting it into the Pauli matrices. So sigma mu alpha alpha dot. And just to be pedantic, to be clear, what I mean by this is p0 plus p3, p1 minus I p2, p1 plus I p2, and p0 minus p3. So you write this 2-by-2 matrix just by dotting it into the Pauli matrices. And there are two observations. Well, so one thing to point out is that if p mu is real, so notice that, nota bene, if p mu is real, R4, then p alpha alpha dot is Hermitian. It's useful to keep that in your back of your mind because I'm going to very quickly become very fast and loose about not having Hermitian momenta to talk about complex momenta. But just to know that when I talk about the p of an external state for a real experiment in real 4 dimensions, you need the you need the p to be a Hermitian matrix. Now, a lot of what's special about this kind of formalism follows from a pretty simple fact, which I'll leave, well, you can easily work out on your own, which is that if you take p mu dot p mu, this is just equal to the determinant of this matrix. And I'm going to put the particle index here. So if you just take the determinant of this matrix, it's a very simple exercise that this is just the 3-1 norm squared of this momentum. So, and that means in particular that if this is equal to 0, then p alpha alpha is not full rank, which is a tautology. So if the determinant of a matrix is 0, it's not a full rank matrix. In this case, it means that it's rank 1 or rank 0. And in particular, if I'd like to come up with variables, so the constraint that p squared is equal to 0 is a constraint on this matrix. I look at Hermitian matrices with vanishing determinant. But if I want to make the fact that the determinant vanishes a triviality, we can just declare, this is again only true for m squared equals 0, here, that it's the outer product of a pair of 2 vectors. And just for these little 2-by-2 indices, the alpha and the alpha dot, both of them run from 1 to 2, I'm going to carry that notation here. So a generic outer product of a pair of 2 vectors will give you a matrix with vanishing determinant. And so these are called spinor variables, and they make this masslessness manifest. Okay. And the way this notation, let's see. Okay. So I'm lost the particle index here, but if I have, so I'm going to say PA, I'm going to associate, for massless, I'm going to associate with a lambda A alpha, a lambda tilde alpha dot A. And notationally, I can write this as an angle bracket and a square bracket. This will be useful in a little bit, and it's related to some notation that's already appeared on the board. So the motivation for using these little brackets and to think about them this way is that Lorentz, the local Lorentz group acts as SU2 left, SU2 right on the alpha indices and the alpha dot indices respectively. So that means that lambda transforms as a fundamental representation of SU2 left, and lambda tilde transforms as a fundamental representation of SU2 right, trivial in the other representations. And that means that Lorentz invariants are constructed out of SU2 invariants built out of the lambdas or the lambda tildes. And in particular, that means that we can write down AB is going to be defined as that. So if you want something that's invariant under the special unitary group, you write down a determinant. There are going to be a lot of determinants in these talks. So that lambda of A and lambda of B is this angle bracket, and it's a Lorentz invariant. Why? Because you hit it with an SU2, it doesn't change the determinant. Special unitary, right? And similarly for the the lambda tildes. So lambda tilde AB is dat lambda tilde A, lambda tilde B. And out of these objects, you can write down familiar Lorentz invariants. For example, PA, if PA and PB are both massless, PA plus PB squared is equal to AB angle bracket, AB square bracket. Okay. Now, some of you, I hope so, at least a couple people in the audience have wondered about my counting of degrees of freedom. So look at a generic pair of two vectors gives you a massless four momentum. Now, that seems to be overcounting, right? I have 2 degrees of freedom, 2 degrees of freedom, and any pair of this vectors like this will give me a massless four momentum. So, but four momentum massless cuts 4 degrees of freedom down to 3. So where's that extra degree of freedom? And that is related to the action of the little group. So there's obviously, in hindsight, an action that you can do on the spinors that leaves this map invariant. In particular, let me erase a little bit here. So Lorentz transformations that leave the momentum invariant have a special name. They're called the little group. Not named after anybody named Little, they're just small. All right, so it's, maybe I should call it lowercase little group. And they're very simple. So all you do is you send, the little group transformations correspond to sending the 8th particle, you rescale by some amount, TA, lambda A, and you simultaneously transform the lambda tilde of the 8th particle to be the inverse of lambda tilde A. And under this map, clearly, the relation between lambdas and p's are left invariant. But the little group does have an effect on wave functions, and in particular, it has an effect then, therefore, on anything that depends on wave functions. So any kind of external observable you might care to talk about. And so in particular, if this is some function of on-shell data, maybe an S matrix doesn't need to be, but if it's a function of wave functions, lambda A, lambda tilde A, that this transforms under this little group to TA to minus 2 times the helicity of that particle, this transformed thing. So TA lambda A, T inverse A lambda tilde A. This is how wave functions transform. And so this turns out to be a very useful constraint on constructing on-shell S matrices. instead of the anchor, the crutch that we have on say, the on-shell Ward identities, we'll have a different kind of consistency check in this formalism that we're talking about something sensible, which will be, in particular, that it's built out of Lorentz invariants. That part is kind of trivial, so there's no Lorentz index here. But also that the function we talk about has the right scaling weights under the little group. So if we have particles with specified helicities, and we build some function out of them, we know that at the end of the day, if we scale all the lambdas in some way and all the lambda tildes in some way, that we pull out an overall factor. And so now if you look at this Park-Taylor formula that's up there on the top of the board, you'll see that if we scale all though notice it doesn't even depend on the lambda tildes. That's not actually strictly true because there's momentum conservation, which I'm going to talk about in a moment here. But has to be something about momentum conservation here. But at least as written there's no lambda tildes appearing at all. And if you scale all the lambdas for the particle 1, say, you'll see that you pick up 4 powers in the numerator and 2 powers in the denominator, because there's one at the beginning and one at the very end. And so this thing scales like t to the minus 2 for particle number 1. It also scales like that for particle number 2, and for every other particle it scales like t to the positive power. And that's one way to see that the function I wrote on the right-hand side is something involving incoming particles with 1 and 2 being negative helicity, and 3 through n being positive helicity incoming, which means they're outgoing with negative helicity. Okay. So it's a useful sanity check at the end of the day. Okay. Now, I've already mentioned momentum conservation, and this is kind of a sneaky way for me it's going to be useful in a moment, but it's also just a sneaky way for me to introduce a concept that will be useful in the next few lectures. And that is just to talk about this physical data for all the particles. So what is a function of? It's a function of all these spinors, a function of these discrete data like the helicities, and then these other quantum numbers. So this I'm about to write right now is mostly, I want to define some notation, and it's a sneaky way for me to introduce something called the Grassmannian. It will play a nice role in the next couple lectures. Okay.
Can I ask you a question about the representation of AB as a determinant?
Yeah.
I mean, I usually write it as the contraction of the Levi-2 tensor.
Oh, great. Yeah, perfect. So, yeah, so
I mean, the determinant would usually have the 1, 1 element in it, not the 2, 2 element.
So I think about this as a matrix formed by 2 column vectors. So what I really mean here, I should maybe spell it out, is that of, maybe I can use the old-fashioned notation. Big thing here. Lambda A, 1 index, lambda B, lambda A, the second component, so it's a 2 vector, and then lambda B1, lambda B2. So the determinant of this 2 by 2 matrix. This is not a dot product or something. So yeah, Lance, of course, is completely right. The determinant can always be viewed as just contraction with Levi-Civita tensors. So what I really mean by this, and maybe I should even put it defined by, is epsilon alpha beta, lambda A alpha, lambda B beta, which is equal to that little determinant there. Okay, so what is the S matrix if you have a lot of particles? What is it a function of? It's a function of all these spinors, these lambdas and lambda tildes. And it'll be useful for me to establish a little bit of notation here, which is by lambda without any indices, what I mean this is a collection of all the components of all of the spinors. So it is a collection of alpha goes from 1 to 2, 1 to 2, and A goes from 1 up to n. And so I can think about this in a few different ways, and I apologize in advance for the pedantry here. I can think of it as a 2 by n matrix, lambda the 1, 1, lambda the 1 particle, its 2 components, lambda n1 and lambda n2. So I can think of it as this 2 by n matrix. I'm going to erase some more. I'm mostly just defining notation here. So when I write a symbol without an index, I really mean all the indices. I mean the matrix, the collection of everything. And if I give you an index, or some indices, I mean marginalize over the other indices. So in particular, I can think about this as a two row vectors, 1, lambda 1, and lambda 2. Or I can think about it as n two vectors, lambda 1, lambda n. So in particular, lambda alpha is an element of Cn. It's an n, it's the row of this matrix. And lambda a is what we've already been thinking about, and that's a 2 vector. There, and similarly for the lambda tildes. So one reason for thinking about this as a 2 vector, or as a 2 by n matrix, is that we can think about how it turns out to be kind of interesting to think about it as a pair of n-dimensional vectors. And the reason is because, what do Lorentz transformations do? Lorentz transformations hit this 2 by n matrix by an SU2, so a special unitary matrix on the left, and just rotates these rows into each other. And what that means is that you have these pair of n-dimensional vectors, lambda 1 and lambda 2, in n dimensions. And SU2 Lorentz transformations rotate them into each other, keeping a unit determinant. So lambda modulo Lorentz. And then if I also modulo by little group, so little group allows you to rescale any of the columns of these things. So little group. This space here is really, we're talking about the span of these two vectors. It's a two-dimensional thing where we can rotate the rows into each other and we can rescale them however we'd like. And so this is really a plane. The geometric thing, this is what this really is the span, the linear span of lambda 1 and lambda 2. And there's a special name for the linear span of a pair of some set of vectors. And in particular, in this case, it's an element of what is called the Grassmannian of two planes in n dimensions. And in general, so Grassmannian, it has nothing to do with anti-commuting variables, but it is the same person, Grassmann. Grassmannian GRKN is the linear span of K, I should say full rank here just for the mathematicians in the audience. I should say full rank, so rank K n vectors. N vectors. Okay, well, there are some that have dual hats that might, I'm still worried about, so. And there's the whole video audience too, so. Okay. So this is a special, it's an example of a space, and we can think about it in lots of different ways. I mean, I think linear span is pretty clear. It's just all of the points, all of the things you can get to by linear combinations of lambda 1 and lambda 2. But you can also think about it as this 2 by n matrix, or in general, a k by n matrix, modulo GLK. So not just SL, but GL. And the GLK transformations allow you to rotate this span into any particular representative of that. And so if we think about the Lorentz invariant content, or the physical data that an experimentalist would really care about, I mean, actually experimentalists usually live in particular Lorentz frames, and so this isn't exactly what the experimentalist would care about. But the Lorentz invariant content of an S matrix is really this 2 by n matrix, this representative of a plane in the Grassmannian GR2n. Now, momentum conservation has an interesting picture in terms of this geometric language. And that follows more or less by just writing out what we mean by momentum conservation. So normally we'd say we have a delta 4 sum over all particles P, A, mu, if they're all incoming or all outgoing I always mean incoming, but it doesn't really matter. And if once we write it in terms of the Pauli matrices, in terms of the spinors, this is a 2 by 2. And I'm always going to be careful, by the way, in this series of lectures. If I have a matrix of delta functions, I'm going to write the sizes of the size of the matrix explicitly. So it's a 2 by 2 matrix of delta functions. Sum over A, P, A, alpha, alpha dot. All right, just because I've converted the single row vectors into, so maybe I should say 4 times 1 here, which of course is just equal to delta 2 by 2, sum over A, lambda tilde A. And because I'm going to get really tired about writing sum over A everywhere, I'm going to introduce a little bit of notation, which is a little cheat, but I hope you will forgive me. I'm just going to define the following notation: delta 2 by 2, lambda dot lambda tilde. And I'm kind of being careful to make it a centered dot, not a lower dot, because this is not matrix multiplication. It's matrix multiplication if you transpose the right thing. So it's so dot throughout these lectures, dot means sum over A index over particle index. Okay? And as a matrix operation, dot means dot transpose, which if I were being very careful in this were LaTeX, precise, I would put lowercase dot for matrix dot. This is an upper dot. Anyway, so this is what the constraint is, and it's a system of 4 different constraints, and it has an interpretation inside the Grassmannian. What it means is that as a pair of 2 planes in n dimensions, lambda and lambda tilde have to be orthogonal to each other as 2 planes. And that has a precise meaning. So that is, what I mean by this is that lambda is in the complement of lambda tilde. So this, what is this? This is an element of GR n minus 2 n. So I could have mentioned this earlier, but for every k plane in n dimensions, there's an obvious complement, which is an n minus k plane in n dimensions. And it corresponds to the space that is not spanned by these k n vectors. So there's a natural duality between k planes and their complements, okay? Which takes this thing, gr n minus k n, which are defined as linear span of not those k vectors. Okay. So that means that we have a 2 plane in n dimensions called lambda, and it has to be spanned by the complement of lambda tilde here, which is an n minus 2 plane. So it's a big thing. It's pretty easy to satisfy that constraint most of the time. And that similarly, lambda tilde has to be inside the complement of lambda as a 2 plane, which is an element of gr n minus 2 n. Okay. So we can think about this as the data that's specifying a momentum conserving set of kinematics is that there's some lambda tilde space here. There's actually a pair of them. This is a 2 plane, alpha dot, which is orthogonal to this. And that means these 4 conditions, that lambda 1 dot lambda tilde dot 1 is equal to 0, et cetera, summing over these A indices, which is just the 4 equations here. Okay. Now, this criteria is this is really just a secret way for me to introduce the Grassmannian, but it actually has one very useful application where this becomes very critical. Can anybody see where this might not be such a trivial constraint? Any ideas? Well, n equals 4, you just have a 2 plane in 4 dimensions, which goes to a 2 plane in 4 dimensions. That's kind of marginal. Close. You're thinking in the right direction, though. Smaller than 4. Yeah, so when n equals 3, something weird has to happen. And that's because you can't have a pair of mutually orthogonal 2 planes in 3 dimensions. This is saying that you have a 2 by 3 matrix and another 2 by 3 matrix that spans rank 4? No, you can't do that. So for n equals 3, you get something very special. And that's, I think, at the core of why there's so much power of talking about the on-shell. It's the foundational fact which will underlie all of the nice things I'm going to tell you about massless theories in 4 dimensions is because the 3-particle S matrix is a little weird. So let's talk about that. Okay. Yeah.
When you do this modeling out, isn't the middle group a subgroup of the Lorentz group? So how do you have to model this out?
You're a little too clever. I'm never really interested in modding out by that. I think the S matrix really does depend on which spinors because you have a reference frame. So I'm being a little cute about this. You could use, in a concrete sense, I could lock the little group. I can rescale the lambdas arbitrarily, but then I'm not really allowed to think of lambda tilde as being an independent matrix, right? Because if I use the little group to scale the lambdas, I don't get to scale the lambda tildes. And so for this discussion, you have to kind of ignore the fact that they're related, and it's still, yeah. So, but good you're paying attention. Okay, so let's talk about what happens for 3 particles. I know that Professor Plefka is going to help me here, but don't. Okay. What? Well, I think it needs to be wet first, right? Yeah. Okay. Okay. The result is beautiful, but it's okay. Okay. So let's talk about 3 massless particles. So and I'm not going to write it, but you should all be very aware that in parentheses here is massless particles in 4D. Massless particles in 4D is what I'm talking about here. Let's give Professor Plefka a hand. Thank you. And I ask for your forgiveness when I tried doing that myself. Okay. Okay. So the basic question is we'd like to write down the S matrix for 3 massless particles in 4D. So we have some particle 1, and it has some helicity. Let's call it H1, some other particle H with helicity 2, and then H3. So it's a generic function of 3 helicities, and it has some other quantum labels on it too. So if we're talking about spin 1 particles, maybe we have to identify which of the 8 gluons in the universe we're talking about. So I'm going to call that the extra quantum numbers A, B, and C. Okay. Now the first point is that momentum conservation for 3 particles is weird. Because we are forbidden from having a pair of two planes in 3 dimensions that are mutually orthogonal, we really have we have 2 discrete cases to consider. Either the lambda in G2n, or it's really the matrices, it's the 2 by n matrix, generic. So it's a full rank 2 by 3 matrix. And then this constraint that lambda tilde is in the complement of lambda perp, which is the span of this vector. And I'll write that out. It's 2, 3, 3, 1, 1, 2. So I might as well just define it to be this. I'm actually giving you a representative matrix. It's not, again, there's a GL1 redundancy here. So I'm going to leave it as a small exercise that I will actually prove on Friday because we need a slightly generalized version of this. It's called Kramer's rule. Sometimes people call this Schouten. But I'm going to leave it as for those who are more ambitious, to prove the fact that lambda 1 alpha 2 3 plus lambda 2 alpha 3 1 plus lambda 3 alpha 1 2 is equal to 0. Which is to say, if you have a generic 2 by 3 matrix lambda, that this 1 by 3 matrix is the unique orthogonal complement of that. Or rather, it spans the orthogonal complement through the origin. Okay? So this has many names. This identity has many names. And in particular, it's kind of an identity you should learn in kindergarten, because what it's telling you is that for two-dimensional vectors, if you have a basis of two-dimensional vectors, you can write lambda 1 inside as components in lambda 2 and lambda 3. So if you have two vectors, they satisfy one relation, which you can think of as representing one vector in terms of the other two, if you'd like. And this is a generalization called Kramer's rule, which we'll review briefly on Friday, because it will be useful for some of our momentum twister notation. But anyway, so this, which is lambda dot lambda perp, if this is lambda perp. Okay, so this is one case. Either lambda tilde is a 1 by 3 matrix, it's a rank 1 matrix, and all the square brackets are 0. So this means, in particular, that AB is equal to 0 for all AB. Or we have the conjugate case, that lambda tilde is an element of GR 2,3 generic, and lambda is completely dictated by being in the orthogonal complement of lambda tilde perp, which is the same thing but with square brackets. So it's 2, 3. I realize that my chalk is not quite as good down here. 3, 1, 1, 2. Now, the important consequence of this is that if you're in case 1, whatever this thing is, it is a function. I put a proportionality sign here because I'm not writing momentum conservation, but that's really it. So it has some non-kinematic dependence on these quantum numbers, A, B, and C, which I'm just going to think of as a matrix of constants. Doesn't depend on momenta. And either it's a function entirely of angle brackets, so it's like f of lambdas, or it's a function of square brackets, lambda tildes. Why? Because again, momentum conservation branches into two branches for three particles. You either have all the square brackets are 0, in which case you're in the top line, or all the angle brackets are 0, and you're in the bottom line. And moreover, we know that whatever function we're going to write down next to this has to scale with the little group as dictated up there. So knowing the helicities, we can actually write down the unique function that we get. So it is, I'm going to be a little explicit in case you're taking notes. So it turns out that the solution to this, there's a unique solution, H3 minus H1 minus H2, 2, 3, H1 minus H2 minus H3, 3, 1, H2 minus H3 minus H1, or square brackets 1, 2, H1 plus H2 minus H3, 2, 3, H2 plus H3 minus H1, 3, 1, H3 plus H1 minus H2. Now, this follows from the fact that there's no combination of these brackets that is little group neutral. Because there's no combination which is neutral under the little group, all of the exponents are uniquely fixed. And moreover, because all the exponents are uniquely fixed, because you can't write down any kind of neutral thing, you can't write down anything that's going to sit inside of a logarithm or anything else. This thing cannot run. So whatever this thing is, it can't depend on the on-shell momenta, because it has nothing to do with kinematics. So the kinematic part, the functional dependence on the momenta, lambdas and lambda tildes, is uniquely fixed. And if as long as I wasn't lying about how the action of little group works, and this general argument holds, then this is fixed to all orders of perturbation theory. The three-particle S matrix is locked. Okay. Now, why don't we learn about this in school? And why didn't this play a big role in our development of our understanding of quantum field theory? And there's one reason which I hope somebody here has been paying attention to, which, remember, if I erased the nota bene, but for real momenta, lambda and lambda tilde are locked to each other. They have to be, in order for P alpha alpha dot to be a Hermitian matrix, lambda and lambda tilde have to be complex conjugates up to a sign. And whether it's plus or minus depends whether it's incoming or outgoing by convention. But they are basically have to be, they're locked into each other. You can't have a solution to momentum conservation like this. This is not possible for real external momenta. In order for this case or this case to be true, the lambdas and lambda tildes have to be doing something very different. They can't be complex conjugates of each other. Which is a long way of saying that the three-particle S, which is, well, not a really long way of saying, but there's an old classic result that I can leave as an exercise, that the three-particle S matrix for real external particles is exactly 0 to all orders of perturbation theory. That is the classic result which sometimes appears in textbooks. And it's not a very exciting result, so you don't learn very much about it. And yes, which is one reason why you start learning about correlation functions and why you start learning about three-particle Feynman diagrams are not the S matrix. Okay, there's a long, interesting story about that. But what we learned here is that if we allow lambda and lambda tilde to not be locked into each other, so, or said another way, if we look at the analytic continuation of the S matrix, then it really is more or less unique. We still have these two branches that we have to talk about, but it's really locked into one case or the other. And in particular, it's a little bit more locked than it at first appears, and the reason is because we'd like it, whatever we have, this analytic continuation of the S matrix, if we take this meromorphic function and we go to real momenta, which means locking the lambdas and lambda tildes into each other, we'd better have the case that this thing vanish smoothly, that it doesn't blow up. We don't want the S matrix to be infinite for real momenta. And that actually dictates something. So if we say that let's say we take this function and we send it to real external momenta, so we say all the angle brackets go to order epsilon, then this thing goes to order epsilon to the minus h, where I'm going to define h to be the sum h2 plus h3. So you can just put all these things equal to epsilon and add up the exponents. And similarly here, if all the square brackets, so if you try to approach the case of external kinematics that are real, this goes to order epsilon, then this thing goes to order epsilon to the h. And in particular, that means that if we have, we'd like this thing to be smooth, then this really can't be some arbitrary combination of them. This really does break up into two distinct cases. One valid for when h is negative, right? If we want this to be smooth, then this has to be the only solution when h is negative. And if we'd like this to be smooth, this has to be the only solution when h is positive. So this S matrix really breaks up into two discrete cases, which I'm going to denote one with a shaded vertex. And I will apologize if I call this thing black. I know that on a blackboard with white chalk, this might look as H1, H2, H3, ABC. Now I can write an equal sign, FABC, and there's a, well, I won't put an equal sign. There's still a proportionality because of momentum conservation. And this is valid when H is less than 0. And then I will have an empty vertex, H1, H2, H3, and this formula is valid, and in principle these things don't need to be the same. A, B, C. So we have two different cases here when H is positive. When H is equal to 0, there are a few cases to consider. So the most trivial case when H is equal to 0, when all the particles are scalars, when all the H's are 0, in which case everything here goes to, that's a constant. This is a constant. So when H is three scalars, this is just constant and constant, and you have, and you can add them together, constant plus constant equals constant, so you don't, no problems there. There are a few other cases like that you could imagine where you actually can't have this property that they would be smooth in this limit. For example, if you had, let's say H1, what if, I'll leave it as a hash thing, because I don't know which case it is right now. But let's say it was like 1 was a scalar particle, and then we had 2 as a plus 1/2, and 3 is a minus 1/2. So this also has the property that the sum of the helicities adds up to 0. It's kind of a weird vertex. This is would look like a term in the Lagrangian that we never write down. And indeed, if you throw it into this formula, what you would find is that this thing would have to be proportional to angle bracket 1, 3 over 1, 2, or square bracket 1, 2 over 1, 3. Neither of which is strictly, well, at least it's not obviously smooth in the limit of everything going real. And we'll see it in a little, well, I will mention why you don't consider vertices like this a little bit later, but at the moment, let's just suffice it to say you've never considered a theory with this kind of three-particle interaction, so let's ignore it for now. It doesn't really matter very much. But one thing that is very nice about this is that regardless of what the helicities are, they could be helicity plus, spin 100 particle. This three-particle S matrix is uniquely fixed to all orders of perturbation theory up to a constant, a real constant, because it cannot depend on the momenta, so it can't run or anything, to some constant, which can depend, of course, on the non-kinematic quantum numbers, like the colors, which gluons you're talking about, things like that. So there's some prefactor there that can depend on the species, but otherwise this is uniquely fixed. Yeah?
Where does the theory come from, the vector theory? So in some sense, if I had young Mills, or if I had young Mills plus an F2 correction, which is not normalizable, but okay, let's say I don't care, where does that enter? Because in some sense, I would expect that you have the two limiting cases, but I can reproduce the same velocity constant if I have. So if I have Q, then I have coupling constant, which has mass dimension. So I can use that to fix the mass dimensions in such a way to reproduce the correct helicity with, let's say, the wrong brackets. For instance, having 1 over the square to get the negative, the positive helicities. So does this, do I have to make any kind of assumption, I don't know, about the normalizability of a theory or about additional kind of constraints, or is it really completely general, complete theory independent?
Well, so the story I've said so far is more or less independent and doesn't, renormalizability doesn't really enter here. But we will learn in a moment, and that's the plan for the next remainder of this talk, is that there are consequences of quantum mechanics that you can't just write down any f's you'd like. Like, for example, this thing, like this 0, 1/2, 1, minus 1/2. This argument doesn't say that this is forbidden. There are other reasons why you can't write down a quantum field theory you care about that has this property. On the subject of renormalizability, it's worth pointing out that the mass dimension of this thing, so F, A, B, C, so the scaling dimension is mass to the 1 minus the absolute value of H. So there is something nice about when the sum of the helicities is 0, because then we get a dimensionless coupling constant. Those are very interesting theories to us. But when it's not, it can be a dimensionful coupling. That's okay. Interesting things about running and renormalizability won't appear at the 3-point level. They'll appear in the UV behavior of 2-to-2 scattering, for example. You'll suddenly realize that there's a UV divergence and that you need renormalization, and all the same story goes through. But it won't appear as a 3-point Feynman diagram that's getting recursed. It's going to be a momentum dependence of 2-to-2 scattering or something else. Yeah? This is the coupling. Well, what would that couple, if I imagine you'd like that coupling to run, if that's what you're thinking. And how would you describe running? So you can't have any dependence on the p's other than what we've written down. So this is a little weird. It's related to this fundamental disconnect that in the Feynman description of quantum field theory, we start with Lagrangian, where the three-particle vertex plays a huge role, and it runs around, but that coupling, the coefficient of the three-point vertex, what we call the coupling constant, is not an S matrix. It's not related to the S matrix. I mean, it is related to the S matrix, sorry, but it's not the coefficient in front of the three-particle S matrix, which is just 0. So the fact that the analytically continued three-particle S matrix is just locked to a constant at first seems at odds with the fact that we think of the three-particle coupling to be running. But the three-particle coupling isn't observable, so why would we care? And indeed, when we look at this in this formalism, if we look at the 2-to-2 scattering for in-Yang mills and pure Yang mills, we'll discover that there's a UV divergence that needs to be regularized or normalized, and that will have a very unusual description in this language. And it won't have the interpretation of changing F. F is locked. It's kind of a different framework. But most of what I'm going to be talking about is tree level, where I can ignore all of these questions entirely. And that's not why I'm restricting myself to tree level, but it is, well, in the interest of time, I'm going to mostly ignore questions about running. And you can just imagine this coupling as whatever coupling you started off when you learned the first half of Peskin and Schroeder, or before you learned about renormalization. Okay, so I just want to, in the remaining time here, I just want to go over a few consequences that you learn from quantum mechanics about what kinds of theories you're allowed to write down. And I'll come back to this in the next lecture, and we'll kind of review it in more detail. But I just want to lay down the key punchlines, which can be found in this paper by Benincasa and Cacciazzo in 2007, 0705, 4305, which lays out some of these kind of beautiful and subtle restrictions on the class of quantum field theories that you could get in this formalism almost for free. And again, I don't have time to walk through the whole argument, but I have enough time to lay out the basic punchlines and some of the results and how you get there. Okay, so this is basic. So I want to talk about this three-particle S matrix, so consequences from quantum mechanics. From QM. So for this part here, suppose all particles have spin s, or sigma. So they're all the same particle. And if you plug that into this expression, what you will find is that this thing, for example, goes to FABC times, if I take the case where this is a plus minus minus, this becomes 2, 3 over 1, 2, 3, 1 to the sigma. Okay, so this is just putting in this formula saying all the h's, so this is the amplitude for H1 is plus sigma, H2 is minus sigma, and H3 is minus sigma. What? Oh, yes, very good. Good. Okay, now one consequence, these are kind of completely trivial, but kind of nice and deep consequences. The first is that if sigma is odd, then I'll kind of leave this as an exercise, but you can kind of already see this thing is antisymmetric under replacing 2 and 3. 2, 3 cubed, so this is a determinant. So if you change 2, 3 to 3, 2, you get a minus sign. If you change 2 and 3 here, it doesn't change anything in the denominator, so you get minus 1 to the power sigma. And that means that FABC, and if you include all the other cases, so this is just, at the moment I'm just showing that B and C it's antisymmetric, is fully antisymmetric. just by Bose symmetry. We have an integer spin particle. We exchange two of the particles. It has to be Bose symmetric. This thing is antisymmetric, so F has to be antisymmetric. Okay? And you can continue this argument in all the other configurations, and you find that it's totally antisymmetric. And if sigma is even, then FABC is fully symmetric. Which is just kind of nice. Now the real juice, and I wish I had a little bit more time, but again, I will come back to this tomorrow, is to think about what, it turns out you can just get a ton of mileage by thinking about this general aspect of what a 3-particle S matrix looks like, and considering what a 4-particle process would behave like on a pole, and thinking about consistency of possible factorizations. So in particular, if you have a process, say, where again all the particles are the same spin, but I'm not going to write the spins here, but let's say it's minus, minus, plus, plus, so it's 1, 2, 3, 4, and you go to a factorization channel, locality in quantum field theory tells us that if P1 plus P2 squared goes to 0, you get a pole, but the residue of that pole has to be the product of 3-particle S matrices. That is what factorization means in a local quantum field theory. 3 plus, 4 plus. And if we think about the helicity configurations here, now locality and unitarity dictates that if we do put this intermediate particle on shell, then because it's on shell, it can travel an arbitrary distance in space and time. And so in any local quantum field theory, the meaning of this picture has to be the product of the two. And we have to sum over all the states that we don't see. So whatever this intermediate on-shell state is, where Pi is P1 plus P2, say, then we need to sum over all the states. And in particular, it can have helicity. And if we only have these particular helicities, this has to be a negative, this shaded vertex, this has to be an empty vertex, and we only have one helicity configuration to exchange. So we get this kind of product of things. And tomorrow I will talk a little bit about the kinematic factor, how this thing looks as a function of spinors, which has a nice story to it. But at the moment, I just want to talk about how the quantum numbers act. Because what it does is it has to be, let's say this is A, B, C, and D, and then this is I. It has to look like sum over all I of FABI, whatever its quantum number is, ICD. So it's proportional to this. And there's a better notation for summing over these indices. Instead of writing dot, because that'll be a little crazy, I'll use Wick rotation that I think everybody knows. So what we find is that whatever this thing is, it has to become some kinematic thing, which is in this proportionality, times this contraction of two of these coefficients. And maybe I'll leave it as an exercise, because it is beautiful for you to discover on your own, and you can use this paper by Benincasa and Cachazo to work out the details. But let me explain some of this first, the simple consequences. So the first consequence is that if you insist that whatever this function is of these 4 states, that it have all 3 of the factorization channels you expect. So it has the P1 plus P2 squared factorization, also the P1 plus P3 squared, the S, T, and U channel. That saying that this function is a meromorphic function of the kinematics demands, for example, that sigma has to be less than or equal to 2. That if sigma is greater than 2, so if it's 3 or 4 or something like that, and you need to know what the kinematic piece is here, but that's called Weinberg's theorem, that higher spin particles don't participate in long-range interactions. And that follows from the fact that you cannot have consistent factorization channels among the S channel, the T channel, and the U channel. For spin 2 and spin 1, you discover something kind of remarkable. In either case, you discover this. And I'm going to change my notation slightly here. I'm going to say my color indices I'm going to write as the particle label. So 1, 2, I can do it the other way. keep consistent notation. FAB dot F dot CD, what you discover is that Cauchy's theorem on the three factorization channels becomes the following statement, that BC dot F dot AD plus F C A dot F dot BD equals 0. And does anybody know a name for this identity, this kind of, the Jacobi identity? And this is just Cauchy's theorem on the three possible factorization channels if you have spin 2 or you have spin 1. Now, if you have spin 1, these things are antisymmetric matrices that participate in a Jacobi identity. That immediately means that whatever these numbers are, these other labels, whatever labels they are, they have to form, by definition, they now form the adjoint representation of some Lie algebra. Which Lie algebra depends on the details here. But the fact that they satisfy in some Jacobi relation means that they form the adjoint representation of some Lie algebra. And for structure constants that are symmetric and satisfy a Jacobi relation is a very trivial class of Lie algebras. In particular, this is a case when it's fully diagonalizable into one-dimensional spaces. And that means that if you have spin 2 particles, so spin 2, even FABC is fully symmetric, you have a Jacobi relation, and symmetric matrices that participate in Jacobi can be trivially diagonalized, and that it does not actually apply what it means that if you have a spin 2 particle, it can talk to itself, and you can diagonalize it so that if there are other 2 spin particles in the universe, they don't talk to each other at all. Graviton 1 talks to graviton 1 and no other gravitons. And this becomes a lot more interesting when you don't consider all of the states in this picture to be the same particle. So for example, if you have 2 gravitons and some 2 particles of different spin, you can derive here, by the same kind of argument, that the graviton the spin 2 particle self-coupling has to be the same as its coupling to every other field. So these Fs really collapse when you have a spin 2 particle around, and this is called the equivalence principle. So if gravitons with the strength of their own self-interaction and their interactions with any other particle are all the same, which is nice. So from this we learned that the only consistent, so this is coming from the consistency of a 4-particle scattering process, not really about the 3-particle. The only thing that went in was just that these things were symmetric or antisymmetric, kind of weak criteria. But we learned that if we have spin 1 particles, Yang-Mills is the unique theory. And if we have spin 2 particles, something like GR, where you have spin 2 particles with universal couplings to themselves and everything else, is the unique theory. Which is kind of a nice consequence, and very hard to prove from the level of Lagrangian, that this is the only conceivable gauge invariant sets of interactions you can write down. So with that, I will wrap things up and take some questions if there's questions. Yeah. Start with it.
One thing that we use is that factorization. So that's the fact of Yang is factorized like this. You can see that that is our new turn going to think locality.
Yeah.
Okay. So what we use is this consistency of this plus locality.
Yeah. So it's a very important point. So this is on some level, this argument is premised on the fact that I have a theory, that I have a 4-particle S matrix that I'm trying to think about that is local. And what I mean by locality is that it factorizes. And then unitarity tells me that factorizing sums over these intermediate states. But I'm really uplifting locality and unitarity to principles, to axioms.
Sometimes I hear that if I have a higher spin than 2, the theory is non-local.
Yeah.
But I don't really understand why you say this.
Sure. So there are a couple things related to higher spin that are that I'm not going to say very much about. But the first thing is that if your theory isn't local, so it's not factorizing like this, like suppose that it was this plus a contact term that just vanished in this limit, or that it was a polynomial behavior or something like that, then, well, then you can evade these arguments, but then the theory isn't local, so okay. So if you're interested in non-local theories, there's a much richer variety allowed to you. And indeed, Weinberg's theorem doesn't tell you that you don't have higher spin particles. I mean, the delta plus plus exists. You can look it up in the part of PDG. It has higher spin. These things exist, but they are massive. They don't factorize. So it's not theories of massless particles that are with long-range interactions. But where the higher spin theories become really interesting is when you evade one assumption that I was talking about here, which is that the states in question are labeled discretely by spins. So if you have, instead of things with fixed spin, if you have continuous spins, infinite spectra of particles with lots of different spins, then you can evade a lot of these things. But then you are, of course, confined to a more interesting kind of theory than, I mean, what we're used to.
Yeah, you said uniquely Yang-Mills theory.
Yeah.
There is this F-cubed interaction with the, so at some point you ruled that out.
Yeah, so that's good. So if I had an F-cubed interaction, at this point, this is where I snuck in the no F-cubed. Because I said there was only this product. And in tomorrow's lecture, I'm going to write down this constant of proportionality, and we'll see where this kind of comes in. But if you had a minus, minus, minus vertex, that is perfectly allowed by this argument. And it does not contribute any poles. It's a polynomial. It's just if you take the minus, minus, minus case here, then it's just angle bracket, angle bracket, angle bracket. So it sneaks through this argument because it doesn't blow up when P1 plus P2 squared equals 0. So I should say that Yang-Mills is unique up to arbitrary things that don't have poles. And then we can talk about those kinds of couplings as well. But if you want to insist on a dimensionless conformal scale, a theory without any dimensionful couplings, then the F cubed is forbidden because it has dimensionful prefactor.
How can you use all of this in a theory which does not have a triple vertex? For example, lambda by 4.
Well, this story is not very I mean, it doesn't have much to say about lambda 5/4, other than that if you have a scalar field in the universe, well, maybe it has something to say about it. If you have a scalar field in the universe, then this would be its unique coupling. It has no kinematic dependence, so it's a little boring. It looks a lot like phi cubed theory. And so you might say something about what the 3-particle S matrix was in that theory, if you cared to talk about it, but of course you don't. So if you had a lambda 5/4 interaction here and you had all these scalars, then the factorizations don't do anything, right? It's just a constant. It turns out that, well, I mean, maybe I should come back to this at a later time, but the short version of this is that 5/4 theory is like the worst case application of all of these ideas. In the best case scenario, if you really like bake everything back into itself, all of the fancy stuff I'm going to derive in the next lecture reproduces the Feynman expansion. So it's like it bought you nothing. And part of that's because there isn't any redundancy to get rid of in 5/4 theory. Feynman diagrams mean more in 5/4 theory than they do in Yang-Mills. In Yang-Mills, they depend on all these gauge redundancies. It's kind of Feynman diagrams are fake, much more fake in Yang-Mills than in scalar 5/4 theory, where you can actually kind of visualize this as a process in space and time.
But as Lance reminded us, there is a 5/4 theory.
There is, yes. It's definitely part of the standard model. And if you want to compute, Higgs goes to 6 Higgses at 3 loops, it's there isn't much. I'm not going to be able to help you much more than Feynman expansion would have helped you. But at 2 loops, that's some interesting. Higgs goes to 6 Higgses at 2 loops is an interesting counterexample to a lot of things.
I guess I'm nominal as the only mathematician in the audience, but I mean, so indeed, in the beginning you said that there's a Hermitian matrix and so on, and then suddenly you talked about complex vectors and so
Yeah.
on. And then you pointed out that, strictly speaking, these vertices don't make sense in for a real Minkowski space. Now, if you were nasty in mathematics, like if you make a wrong assumption, you can prove anything. It's part of it.
Yeah.
So how do you know that somehow you can really trust your results and yet you get the Minkowski space?
That's great. That's a great question. So, and it's important to, I think it's an important foundational attitude about all of these like new developments in quantum field theory, that we are absolutely reproducing the Feynman expansion. Like we're not changing the output of quantum field theory. We're just trying to capture it in a different way. And so, you know, for this three-particle S matrix, it's a little bit weird because we're talking about something that's exactly zero, and I'm saying if you analytically continue something, it's something else.
But it's not exactly, it's an analytic continuation in some high-dimension complex space or some high-dimension real space. It's not the usual analytic.
It's not, yeah, it's not the usual analytic continuation. So so for the three-particle S matrix, I don't know where you can have a kind of a philosophical debate about it, but when I compute things more like this, so this is where it starts becoming meaningful. So for this process, I can talk about this factorization with all the four particles to be real. And what I find is that it's only the internal state that's complex. So the internal one has to be complex, but these things can all be real. And when I start looking at box, you know, more complicated diagrams like I'll be drawing tomorrow. Oh, you're right. It's not. Yeah, okay. Yeah, okay. You're right. Sorry, but like let me draw one where it's legitimately going to happen. So I have four external states here, and I solve these four on-shell conditions. These are four massless particles. You find that there are two solutions to cutting these four propagators. They're complex solutions. And it's the S matrices that we're going to write down will allow the external states to be real. It's just that they're being built out of objects where there's a lot of complex things in the middle. I don't have a great answer to that. It's an important criteria for me that when you restrict to real external kinematics, you reproduce exactly the same meromorphic functions that you would have gotten from the Feynman expansion. Yeah. Sure. So very little about what I've said changes. You can still have real momenta. I mean, so at some stage, I'm kind of ignoring the signature, and I'm just going to be talking about these abstract functions of lambda and lambda tilde. And then what space-time signature you're in, I'm going to recast as a criteria of what lambdas and lambda tildes you care about in the external states. So for 2-2 signature, the lambdas and lambda tildes are independent and real. For real 2-2 signature. For real 3-1, they're non-independent and they're both complex and they're complex conjugates. So you have 2 degrees of freedom, because it's a complex 2 times 2 degrees of freedom modulo little group. So you have lambdas more or less and not lambda tildes, or vice versa. And for 4-0, you have, it's another case still. So, but I'm just going to write down some meromorphic functions of lambdas and lambda tildes, and you can put in whatever ones you'd like. Yeah. Okay. Great.
Thank you very much for your great
Thank you.
break until 2 o'clock.